much for coming to the second installment of this semester's distinguished lecture series. And we're delighted to have Avi Wigderson here. Avi is somebody who's made amazing contributions. Actually, I was looking at Google Scholar today and was reminded again just how many different areas Avi has contributed to. Circuit lower bounds, parallel algorithms, logic, graph theory, doing constructions of expander graphs, de-randomization, which is the process of taking a probabilistic algorithm and turning it into a deterministic algorithm, distributed computing, interactive proofs, zero-knowledge proofs, other areas of complexity theory. A general rule, actually, is that if you look and see where Avi Wigderson is working, well, that is the area of computer science where some of the most exciting progress and deepest insights are being made. And this is a pattern that's held up over the last few decades, actually. Avi got his degree from Princeton in 1983, spent quite a bit of time in Israel and the Hebrew University, and has, as well as making distinguished contributions to computer science and the research sector, has also been very productive as an educator. He is a PhD advisor for a great many people who now are among the leaders in the field. Also, I should mention that, certainly I should mention where he is now. He's at the Institute for Advanced Study in Princeton, and there he has taken the leadership, one of the leadership roles in a brand new NSF-funded intractability center that is joined with Princeton University and the Institute for Advanced Study and NYU and also Rutgers. I've talked long enough, and we should now get ready to enjoy Avi's talk on the art of reduction.
What's my remote? Okay, so what I want to talk about is reductions in theoretical computer science, but sort of the broader message that will not be hiding very deep, I'll repeat it again and again, is that often sources of ideas, in particular here for reductions and in general for progress, in research often come from doing other things than what you are really trying to do, or at least having other people do other things, and you just should keep aware of these developments, and often these really strange and surprising connections lead to obtaining deep results. So I want to talk about reductions. So what's a reduction? We are in complexity theory. We want to know how difficult is it to solve problem A. And sometimes we know, we have an algorithm for it, for example, but sometimes we don't. And the next best thing, if we don't know, but we have two problems, A and B, we may be interested to know what's the relative difficulty, namely, is one at least as hard as the other. So a reduction is an efficient algorithm for A. If you have one, then it implies an efficient algorithm for B. So that's commonly used in programming practice, right? A would be a subroutine in the solution for B. And it has, if you have such a reduction, it has two consequences, equivalent consequences, but often it's good to separate them. One is that if A is easy, then B is easy too. Okay, not much harder. And the other consequence, just a contrapositive, is that if B is hard, that implies that A is hard. Right? So even though they are the same, logically equivalent, sometimes you use the reduction for this purpose, and sometimes you use it for this purpose. So there are many reductions, and for many problems, let me give you just two problems whose status, whose difficulty we don't really know. And they are very, very important problems. They are of the variety called constraint satisfaction problems that arise everywhere in computer science and actually outside of computer science. And these two examples are the following, two problems are the following. One is the famous three-sub problem, in which you are given a bunch of Boolean constraints. They are written as, clauses of three variables, just disjunctions of three variables. You have many such disjunctions. And you are trying to find a Boolean assignment, just a truth value for each variable, in such a way that all these constraints are satisfied. That's a three-sub problem. Another constraint satisfaction problem, also famous, is the three-coloring problem, in which you are given a graph, an undirected graph, and here constraints are on pairs of variables. Okay, and what you're supposed to do is to assign one of these three colors, yellow, orange, pink, to the vertices of this graph, and in such a way that adjacent vertices should get different colors. That's a very, very common resource allocation. And you're supposed to satisfy all constraints. It should be a legal coloring of this graph. Okay, and we don't know the complexity. We think both are hard, but we don't really know. They are very important practical problems, so there was a lot of effort devoted to solving them. And in the early 70s, there were amazing breakthroughs that really changed the face of the field, and they came with the definition of NP and NP completeness. First, the result by Cook and Levin that the first problem, 3 subs, is NP complete. And then Karp's paper showing that 3 coloring and many other problems are NP complete. So let me tell you just a little bit about one of these proofs, because it's a reduction of the type that is extremely common, and we will not devote the talk to them. So, but let me just to make sure everybody, has seen it or will recall that has seen it in some undergraduate class. So, what did Karp actually prove? He gave a reduction. He showed that, so this statement, for this statement given that theorem, it's enough to show the following, that if you have an algorithm for 3 coloring a graph, then you also have an algorithm for satisfying Boolean constraints. And people who have never seen this, it's really amazing. I mean, the two problems look completely, different languages, different, of different nature. And it's not clear at all that such a statement, that there is any connection between them. But in fact, that was the great thing about this paper of Karp, was to show that reductions exist between very different natured problems. And let me tell you roughly how this reduction goes. So you want to solve a 3-sub problem, so you're given a formula, a conjunction of clauses, you want to satisfy them simultaneously, and you already have in your pocket an algorithm for 3 coloring. What do? Well, you want to use it, so you translate your formula into a graph, and the translation is such that when you get back from this hypothetical algorithm a legal coloring, you can convert it back to satisfying assignment. That's a reduction. And the way, so that's just saying what should happen, but how do you do it? And the insight is that it's sufficient to do it for very small formulas. If you do it for this formula, if you just find a graph that will solve this very simple satisfiability problem, then in fact you can find it for all formula just by the virtue of formulas being built out of n's and o's. So that's what you want to do. What's a graph that will somehow, every legal coloring of it will supply a solution to this? Turns out that I think that's the simplest I know. So it's not so easy to find. What is going on here? It's a graph. You don't have to try to understand it. Let me tell you what it does. Suppose that these are your 3 colors, and suppose we just decide to call yellow 2 and pink 4. That's just an arbitrary decision. If you look at this graph, put these 3 colors there. It's a triangle, so it has to get 3 distinct colors. And we just think of the variables x, y, and z sitting in these vertices. So whatever coloring these vertices will be, should be the truth values they get. And it turns out that in every legal 3 coloring of this graph, these 3 particular vertices will always get a truth value, namely one of those two colors. And in fact, in every coloring, this will be satisfied. Z, the color here, will be the disjunction of the truth values of the colors. So it works, and because it works in general for every formula, and it solves this problem. It gives this very strange translation between these two different looking problems. And that's called the gadget reduction. It's a gadget reduction because once you do it for some finite size problem, then you can extrapolate and do it for all problems. And again, I repeat, it's very ingenious, and when it was first done, it was really amazing. But today, there are thousands of reductions like that are performed every day. In fact, in Papadimutrlou's language, this is the greatest intellectual export of CS to math and science. But first it was an export from theoretical computer science to practical computer science. And of course, programmers were using anti-completeness, let's say, to justify the difficulty of finding efficient algorithms. But it's really going outside the field, and he likes to say that Google Scholar was mentioned already. He searched for papers containing, so in survey talks he gives, he likes to make this point that type on Google Scholar, look for papers with the title NP-complete, just to sort of see the impact of this notion. And you get 2,000 titles. And everybody should be impressed. He said, no, wait, this is not what's impressive. The impressive thing is that I restricted the search. So, and that's true, and it's really amazing. What these are not proven by computer scientists. These results, these NP-completeness results, are proven by these people. So it shows you several things. A, that the mechanics of these reductions is by now understood by thousands of people in other disciplines. And the other, that they really care about this. Why do they care about this? Because, well, maybe for us, for computer scientists, NP-completeness is used to state computational difficulty. That's a mark of difficulty. And for them, and it turns out to be extremely useful, is typically structural difficulty, or structural nastiness in the structures they try to understand. And most of them, as I said, are gadget reductions, and gadget reductions by now are, well, of course, the problem has to be NP-complete to begin with, but if it is, almost surely you will find a gadget reduction showing it, and many people are capable of doing that. Okay, so the reductions I want to tell you about are of different nature, so let me go back to the problems we discussed, and in particular the three sub-problems. Okay, so the fact that it's NP-complete doesn't make it go away. People do need to solve these kind of problems in all these areas. So what do you do? So it's hard. So one relaxation, you might say, is to say, well, okay, maybe I cannot find efficiently a solution satisfying all constraints. I'll try to find some that satisfies most constraints or many constraints. Okay, that's a very natural relaxation, practical. So that's what we are trying to do. So what would be an algorithm that satisfies many constraints? I claim that there is a very simple algorithm to satisfy 7/8 of all constraints. And in fact, this can be done in every formula, whether satisfiable or not. So 7/8 is always easy. Why is it easy? Anybody wants to give an answer? How would you satisfy many constraints? Yeah, random. Yeah. Pick values, truth values randomly to these variables. In every constraint, there is only one of the 8 possibilities that's forbidden, right? If all of them are false. So with probability 7/8, it will be satisfied by linearity of expectation. This will be true in general. So you can, with a random assignment, you can satisfy 7/8. So the most trivial algorithm, if you will. And in fact, you don't even need randomness. There's a very simple deterministic algorithm that will satisfy 7/8. So the question is, okay, if it's so easy to do 7/8, we probably can do with a slightly smarter algorithm, we can do better. So let's try to do better. How much better can we do efficiently? And here's the result I want to talk about. It's the result of Hastad from a few years ago, showing that there's no hope of doing better. So the problem of doing slightly better, and epsilon better for any constant epsilon, better than 7/8, is still NP complete. It's as hard as satisfying all of them. So it's amazing in several respects, most of which I'll talk about later, but just one of them is that we know exactly the limit on the hardness of approximation of this function. So standard NP completeness results over several decades mainly talked about achieving the optimal value. This and the other results I'll talk about now are about the hardness of even approximating and trying to find exactly how far you can approximate these problems efficiently. And the proof of this theorem is, will be the subject of the talk, but it's related to the PCP theorem, which I'm sure many of you heard of, and I'll explain later what it is. So it's a really complex web of reductions that eventually lead to this, but the summary of it all, one line summary, is it's a reduction, not between two optimization problems like we saw before, but between two versions of the same problem. One is approximation and one is exact. So what Hastad showed is that any non-trivial approximation to 3SAT, better 7/8 plus epsilon, can be reduced. So if you have a good algorithm for this, you can get a good algorithm for optimally solving 3SAT. And the reduction is far from a gadget reduction. And in fact, the thing that comes here is interactive proof that I'll tell you about. So something very new and unrelated to the question at hand. Okay, so that's what we are going to talk about. Let me tell you the plan of the talk. It's not yet the plan. So we want to get here. We want to prove that 3SAT is, how to approximate even 7/8 plus epsilon. That's where we stood 30 years ago. 30 years before Hastad. We knew that optimally it was hard, it was NP hard. And actually, this 30-year gap was bridged by this intermediate, very important result. Was the first inapproximability result for 3SAT. It was not optimal. It was just said that 0.99 is hard to achieve. And as it turns out, going from here to here took about a decade, and going from here to here took about 2 decades. So I'll try to explain in 5 minutes something that happened in this decade to show you the type of things that need to go into the proof of Hastad. And then I'll tell you in about 20 minutes what went on in these 2 decades that allowed for this. Okay? Questions so far? Okay, so the little piece of the puzzle here that I want to tell you about is this influences of Boolean function. Again, I stress it's a different, it's unrelated, so to speak, to the approximation questions. It's a different question. It comes motivated from distributed computing. But anyway, it was essential to make progress on this question. To solve this problem was very important for Hastad and other inapproximability results. So let me tell you in one slide about that. Okay, so what are influences in Boolean function? So here's the game. Was introduced in a very influential paper of Benor and Lineal in the 80s. And the idea is the following. You want to achieve some decision-making scenarios. Here's a very simple one. You want a bunch of people, like all of us in the room, want to agree on a coin flip. So we want it to be random, but we want that nobody will be able to have his favorite random outcome come out of this decision making. Another way to think about it is that you want to decide a good election scheme in a way that let's say if all players are picking their votes randomly, no player has too much influence on the outcome. And so what's a good way to think about? We have a bunch of players, and each of them can toss a coin, can decide his own vote, his own random coin separately, and then they want to combine the results, a vote. And they can combine it any way. I mean, they just can take some function, evaluate this function, Boolean function, it will give a bit, and you want this bit to be influenced as little as possible by any single player who may want to influence. Okay, so let's see some examples. Here's a really bad one, maybe certainly the worst one. The parity function. So they toss coins, they are bits, and then they compute the parity function. Well, if this guy just waits for the others to see the other votes, and this is, by the way, it's a public information model. There are no secrets here. This is a game without cryptography. Okay. So he sees all the votes, and then, casts his own vote so as to get the result here any way he likes. And in fact, every player has influence one in this function. It's the worst. Every player completely controls this function. It's a lousy voting system. And I don't think it's used too much. The really natural one is, of course, the majority function, which is used in lots of elections, lots of countries. And then let's think about, I think I have 9 people here, so in this game. So when will a player have influence if the others are tossing the coin? Well, the last player has influence only if the others are just balanced, half-half. And the probability of this in 9 players is about root n. In 9 players, it's about 1/7. I mean, they are constant. So that's good, we want, there are 9 players, we hope that no one will have influence more than 1/9. So in this gets close. But 1/root n is not 1/n, so it's a little misleading. So are there better functions? What do you think? Or majority is the best? Yeah? Nobody what? What?
Constant 0.
It's the outcome. You want the outcome to be unbiased. You want the outcome to be. Let's say all of them really toss coins. You want so you cannot take a constant function. Function has to be half-half. Yeah. So actually, there is a better function. Actually, the Electoral College somehow people like to calm down on. Majority of majorities is a better function. Turns out. And in this case, you get the influence is about 1/8, and you can calculate it asymptotically. It's still far from 1/n, but it's better. So now, do you think there is a better? Can we achieve 1/n? Yeah, people don't like to commit. Here's an amazing result by Khan-Kalayan-Lineal that says that no, there is no optimal function. You can, in every function you pick, there will always be a player with very unproportional influence, log n/n. So asymptotically much better than what you could hope for, 1/n. There's always a player that has influence much more than he or she deserves. And in fact, the consequence of this is that there's always a coalition of about n/log n players that have complete control over the elections, no matter what election scheme you choose. So that's a really fundamental problem. And not only is the result surprising and interesting for game theory and other aspects, but also the proof is really ingenious and uses tools that are, by now became standard, but they were non-standard in this game, but harmonic analysis. And these tools are exactly, this type of results and these tools are exactly the type of results that Hastad uses exact inapproximability results, starting from some inapproximability, getting exact inapproximability results. I will not say more about this, but questions about? Okay, so you see for this progress, something very remote had to happen. Now we want to talk about what had to happen for this result, the first non-trivial inapproximability result. for systems. So what had to happen is basically the invention and the study of probabilistic interactive proofs. And I'll talk about three types of proof systems like it. Okay, they are the main ones really. One is called IP. They are all generalizations or at least I can think of them, of the NPS proof system. One is IP, it's called interactive proofs. The other is 2IP, two-prover interactive proofs. And the third is PCP, which is probabilistically checkable proofs. I'll define them all. But just to summarize what I'm going to say in the next 15 or 20 minutes, is that to tell you, well, of course it cannot be clear now why they are related to this problem. They seem to talk about, again, different issues. So they came to be for reasons that have nothing to do with optimization, and that's what I want to summarize now. So these two classes of proof systems arose from cryptography, and I'll explain how, and in particular from the attempt to understand what's called zero-knowledge proof. And that led to their definition and their study, but understanding their power took a long time until another field was developed, which is a field of program testing and checking, which brought forth the technique of arithmetization. And once this technique existed, then this study was, giving results about the power of this. And it turned out that these classes of proof systems turned out to be equal to well-known studied classes in complexity theory: polynomial space computation, non-deterministic exponential time computation. And only at this point was the connection to approximation made. And it became sort of essential to tighten parameters, and when they were tight enough, this was proved to be equal to NP, which is more or less equivalent to this statement. Okay, so this picture I'll try to now do in a little more detail. Questions about? Okay, so I want to tell you about probabilistic proof systems, this somehow essential notion that had to be developed to bring about these approximability results. And this came from the very fertile mind of these people, actually in two independent papers, Baba and Goldwasser-Micali-Rackoff. And to define interactive proofs, first let's define normal proofs, namely NP proofs. NP proofs, the class NP, when do you say that a problem or a language is in NP? A problem is in NP if, there's an easy way to convince somebody else that it is in the language. So in this case, you can view it as the interaction between a prover and verifier, but a very simple interaction, like in mathematics. The prover just sits at home for several years, like in this case, and at the end publishes a paper and submits it to a journal, and that's the proof. And then any verification procedure can just check it. Okay. And you accept, you decide that X is in the language if the proof is good. That's an NP proof. That's standard proof. They are one shot. There is no interaction. They are deterministic, and we are familiar with them whenever we send a paper to a journal. What is the probabilistic proof? The probabilistic proof and interactive is more like the Socratic method. You go through a long process of questions and answers in order to get to the truth. So you have like before, a prover and a verifier. But the verifier is not satisfied just with the paper, She, in this case, would keep asking questions. I don't understand this, explain to me that. Maybe she tosses coins and asks random questions about other things. But at the end, like before, she must decide whether she believes X is in the language or not. And if there is a convincing proof in the sense that X is in the language if and only if she accepts such an interaction, such a conversation, then we say that this language is in IP, in the class of interactive proofs. So this class is an obvious generalization of this class, right? You allow both interaction and randomness, which here are not allowed. Okay, so in principle, there are more languages that can be proved in this model. At this point, especially the mathematicians should ask, what kind of proof system is it? I mean, proofs are about the truth. If you have a randomized procedure, there are errors. We don't want errors, we want the absolute truth. So the answer to this is that this proof system was not designed to decide the Riemann hypothesis. It was designed for cryptographic protocols where the type of statements we make is, I chose the 2 primes and multiplied them, or I did, It's not about the truth of some, everlasting fact. It's just about things I just encrypted my credit card according to your specification. So it's not, it's just for practical purposes, and there we are willing to tolerate error, especially if we can make it really, really small. Okay? So, and in particular, the type of properties, so we accept some tiny probability of error, and what do we hope to gain? We hope to gain properties of such proof systems that are, cannot be obtained in these proof systems. Because in this proof system, if Wild's proof is Fermat's theorem and sent it to everybody to read, then we don't only know that Fermat's last theorem is true, but we also know the proof. We know exactly what he was thinking about and how he proved it. But in cryptography, often that would be a secret you are not willing to share with others. So in cryptography, you would like zero knowledge proof. And that was really the motivation of introducing interactive proof in this paper. So what is a zero knowledge proof? When do we say that a language has a zero knowledge proof? It has zero knowledge proof if the prover and verifier are going through the same interaction in which the prover is trying to convince the verifier that some X is in the language, about the truth of some statement, but on top of the usual property that the verifier accepts if and only if X is in the language, we further want to ensure that no other information is gained by the verifier. Nothing else. Okay. So this seems pretty ridiculous, because when did you last convince somebody to switch their mind, to change their opinion about something without giving them information? Or how can Wiles convince the mathematical world that he has a proof of Fermat without showing them any detail of the proof? So it looks a little ridiculous. It's certainly nice to have it in cryptography, but it's not ridiculous at all, and in fact it's the opposite of ridiculous. It's universal. It can always be done. So what we proved a little bit after that is that if one-way functions exist, so that's a standard assumption in cryptography. If one-way functions exist, then everything in NP, everything which can be proved in a standard way, can actually be proved in a zero-knowledge interactive proof. Okay? So every proof can be made into a zero-knowledge proof, and that's very important for cryptographic protocols. So that's nice. And then the question is, we want zero knowledge. Of course, these one-way functions are standard in cryptography, so it's not a big assumption given that we are doing cryptography, but the question is whether they are necessary, or whether there is since we change the model, we introduce interactive proof. Maybe there is a way in which we, don't need it or need less. It turns out that in this model it's impossible. One-way functions and zero knowledge are equivalent. So you cannot get rid of this assumption. What do you mean you cannot get rid? Well, maybe you can get rid, and in fact, if you change the model, so let's change the model again. Let's enlarge the variety of proof systems that we are willing to accept. So let's assume that instead of one credit card you put in the ATM machine to convince it to give you money, you have two of them, and you have two credit cards, so the two provers that are trying to convince the ATM to give you money. And that's the two-prover interactive proof model, in which, again, there is a verifier. She wants to learn whether X is in the language, whether I am Avi. And she talks to two provers who are physically separated. Okay, so they cannot talk to each other. They cannot learn what questions she's asking each of them. And she interacts with both of them, and at the end, like before, she decides whether she believes them, and X is in, a language is in this proof system class if the verifier accepts with high probability, if and only if it is a true statement, X is in the language. And it's a more powerful proof system. It has two provers now. And it turns out, and this was really the motivation for defining this proof system, is that in this proof system we could prove that NP can be, so everything you can prove at zero knowledge, and there is no assumption. You don't need one-way functions or anything. This computational assumption was replaced by an assumption about the physical separation of these two provers. And actually, the institutions we were at the time thought that it was an idea that will make a lot of money, and against our protest submitted a patent on this, which we never saw a penny of course. So, but it had theoretical value, and that's what I want to talk about now. So we have, the standard thing that happens in theoretical computer science. You define new models with motivation, in that case from cryptography and from zero knowledge. But now you have them and you just study their power intrinsically. I mean, what is, and that's of course a very natural question for computer science. What's the power of randomness and of interaction for proof systems? And there are obvious statements you can make. So certainly these two classes that we defined, they are generalizations of NP. So we have IP and we have 2IP. And there are also obvious upper bounds on their power. It was not hard, it was shown very quickly. IP is at most polynomial space. It can be simulated in polynomial space. 2IP is simulatable in non-deterministic exponential time. So somehow limits on how big these classes are were known. And also there were, few examples of problems that seem to be, seem to need this power. Maybe they're all NP, but it seems, so this particular problem, just known isomorphism and a couple others were known to be in this class and not known to be in this class. And then, most people believe that these inclusions were very strict and these classes are very close to NP. And a few years passed by without nothing happening because, again, something had to happen elsewhere. And in this, like I should have yellow worlds floating around the screen, in a different galaxy, which actually is Berkeley, Manuel Blum and his students were going into this area of self-testing of correcting of programs. So let me explain to you about this. So once again, it's sort of a twist on a program testing problem in which you are given a program for some function. Let's say it's over some field, f to the n to f, n variate function, and you have your input. You want to run the program and get the output as usual. The problem with programs is that they can have errors, right? So you somehow trust that there are very few errors. Maybe like the Intel chip with the division. It does the job most of the time, but you don't care about most of the time. You just want it to be correct on your input. You can err on everything else as far as you are concerned. You just want to make sure that it gets the right answer for your input. Okay. So what do you do? Well, what they started studying is for which classes of functions can you do something at all. Okay? And here's an easy case which I'll describe. And that's a case that G, the function computed by this program, is a linear function. You don't know which linear function is computed, but you know that it's a linear function. So linear means it satisfies this obvious equation. And in this case, there is a very simple solution if you know that it errs let's say, at most a fraction 8 of the space. 8 is a lot, right? Even then, you can do something very simple. Here's what you do. You want the value at x, but what you actually ask the program to do is to compute the value at 2 random points. You pick a y at random, and you ask the value at y, and the value at x plus y. And then you use linearity, because, okay, the program is, makes an error somewhere, right? Maybe even on your x, but you pick 2 random values, y and x plus y, and with some good probability, actually, it's 1/8 for each of them, so it's most a quarter that they both land, that one of them lands in the bad region. And other than that, you can use linearity and just subtract p of y from p of x plus y. That would give you g of x, the right value, with probability at least 3/4. And if you want better probability, you can repeat it several times and take majority. So that's wonderful, but of course for very restricted type of functions, most programs don't compute linear functions. But it turns out that this is a very powerful idea, and in fact, a few years later, Beaver and Feigenbaum found out that it generalizes to a very complex function, not linear function, complex, the permanent. I'll talk about it in a second. And Lipton, Beaver, Feigenbaum, and Lipton, and then to all low-degree polynomials. So what is the value of that? So you can do the same type of randomizing your input and sending it somewhere and collecting the results and get with high probability the value you want for other more complex functions. And first, let me say what happens in this in the example we saw, and also in the permanent. So for the this is more important. The permanent is a function of matrices, very much like determinant. The formula is written here, and you see that like determinant, only we don't have the sign of the permutation. And unlike determinant, it's a very hard function. It's a function that's harder than NP-complete. So what this procedure does for the permanent or for the linear functions is that we understand now that if it can be computed by an erroneous program, we can build from an erroneous program a correct program. So if we can solve it for most inputs, we can solve it for all inputs. Okay? So it's a statement connecting the worst case and the average case behavior of this function. If it's, so taking the contrapositive, if it's hard in the worst case, it's hard also on the average case. And this is called worst case to average case reductions. It works for any low degree polynomial, and it's a different kind of reduction than the one we solved, and it's very important. And the key to it is this arithmetization technique, which takes Boolean functions and converts them into polynomials over fields in which computation is more robust, in which you can tolerate errors. Okay? And that technique, once it was around, suddenly people realized that, wow, that's the key to understanding interactive proofs. Then there was this avalanche of results with a very, very short amount of time. Noam Nissan realized that you can solve this permanent. You have interactive proofs for it. So remember, permanent is above NP-complete. And suddenly there were some kinds of proofs for it. So that was really surprising. And quickly afterwards, in this joint paper, they showed that the permanent and actually these classes, for example, Cohen P, are in IP. So there are lots of acronyms. I'll explain them in a second. But for those who follow it, then quickly afterwards, Shamir determined the exact power of the interactive proof class IP. Then Rabbi Faulkner-Lund exactly understood the power of 2IP. And then a little later came the PCP theorem. So you can think of this as a bunch of acronyms. That's wrong. Every one of these results carry a really very basic and very fundamental intellectual or philosophical content. So let me tell you about some of them. So this first result about Cohen P has interactive proof. So Cohen P is the set of tautologies, a set of formulas without an assignment. So these are the kind of things. How do you prove that formula does not have an assignment. It seems like you have to go over all possible assignments. So it doesn't seem to possess short proofs, but nevertheless, if you are willing to allow probabilistic interactive proofs, then you have short proofs with tautologies. So somehow the universal quantifier can be replaced by an existential quantifier, namely a proof, if you have probabilistic interaction. That's the first result. What about Shamir's IP equal P space result, which actually is much stronger than this? Where it lifts not just universal quantifiers, it lifts it to strategies in games, alternation of quantifiers. Because P space, I should say, P space is the computational home of all games, of all strategies. So typically, chess, Go, all the games are computational in P space. And what this says is that optimal strategies for games can be efficiently proven. And, if you think of chess and you think of this exponential search tree that, different programs for chess are going through, somehow you can prove it. Well, let's say a Martian came here today and claimed that let's say it, has an optimal, as white, he always wins. And, we are mortals, we can run our best programs or our best Kasparovs, and, but we don't know that they are optimal. So we can play against him. But how do we know that, and maybe he wins, how do we know that, how can we check his, assertion? Well, it turns out that Shamir's result gives a way to check his assertion, right? Because it says there are efficient proofs of optimal strategies. And in fact, the way the proof of this theorem goes, I'll tell you how the Martian can convince us. The proof of this statement is of the following nature. Take any game. It can be converted to another, chess, for example. It can be converted to another game, which we can also play on maybe a slightly larger board, okay? And in that game, one player, us, the stupid ones, an optimal strategy for us is random play. And now we play randomly against him, and if he consistently wins, he has a winning strategy. What about this result, about the power of two-prover interactive proof? What can be the intellectual content of this? Well, this took time to understand, and this wonderful paper of Feige, Goldwasser, Lovász, Safra, and Szegedy eventually made the connection that we have been talking about from the beginning back to approximation. It turns out, even though it doesn't look it turns out that this is a statement about the hardness of approximation of the clique problem, and later was of other problems. So here was this leap was made. Okay, good. So I have about 10 minutes or something. Yeah. And as I said, once this connection to approximation was understood, then an effort was made to really tighten the parameters. This connection, which I'm not explaining, becomes better and better the more efficient the proofs are. And here are the type of proofs you really want. And I'll describe the PCP. This last probabilistically checkable probabilistic proof class, it's called probabilistically checkable proof. And this class has no interaction. We are back to the model in which you just write your proof down and somebody looks at it. So let's recall again what was NP in this language. In NP, we had a prover, a verifier. The prover wrote a proof down, a witness, and the verifier just checked it, looked at the input, looked at the proof, and checked it. But in NP, standard NP, the verifier can read the whole proof. And in PCP, the verifier is restricted to read, let's say, 10 bits of the proof. So even if Wild wrote 300 pages of complex mathematics, the referee of this paper is allowed to just sample 10 bits in 10 random pages, look at them, and then decide if the proof is correct or not. And again, this looks completely ridiculous. I mean, how can you catch a bug if you in a proof? But of course, we don't have to use the same proof. The question is whether there are proofs that allow such spot checking that will guarantee with high probability that the proof is correct. And again, as ridiculous as it may look, it is universal. And that's the famous PCP theorem of Aurora Safran, Aurora Lon Matwani, Sudan, and Segedi. Mario is here, by the way. Guys, all the I keep mentioning it. The PCP theorem, and again, it's another kind of reduction. It's a reduction about making proofs robust proofs. They are robust in the sense, what does it mean that you can check them by spot checking, by looking at very few bits? It means that if there was a bug in a proof, it becomes, after this transformation, it becomes spread out everywhere so that you can check it. You will catch it almost surely. Okay, so that's the PCP theorem. And that's the culmination of this 2 decades that led from the hardness of stuff to the hardness of approximating stuff. So it turns out that it has this interpretation, which I'm not going to explain. And the last 5 minutes, I want to mention something, again, completely different. And I know some people in the audience who had the pleasure of teaching this theorem. And I certainly have gone through this a couple of times. It's really hard. That's probably one of the most difficult theorems in theoretical computer science. It's really intricate. It uses lots of algebraic ideas. It has, it's really complex. And the shortest write-ups of it are really long. And it takes a month or something like this, and not with all details if you want to do in class, even in graduate class. So people were trying to simplify it, and people kept simplifying it, but it still looked roughly the same. And it was frustrating that we didn't have a sort of a better or clearer understanding of this very fundamental theorem. And this was like that for about 15 years, and last year, roughly, Irit Dinur managed to give a completely different proof of this theorem. And she did it in using what's maybe called gap amplification. So what I want to say in the last few minutes is tell you something about her wonderful proof. So in this story that I told you, the original proof and all subsequent simplifications of it went in this route, and in the algebraic way, went through algebraic techniques. And what she was doing is she said, well, we have it's a completely different proof. It's a combinatorial proof. And the idea was that we want to prove constant hardness of this satisfying clauses. We want to say that you cannot satisfy a constant close to one fraction. And one way to start it is to say, well, this is proved by gap amplification, is to say that this hardness really means that you cannot distinguish the situation where you can satisfy the formula or you can not satisfy it, but maybe you can satisfy all but one. And this gap of 1 over n that you start with, you want to build it and build it higher and higher until it becomes a constant gap, constant fraction. And she found a way to amplify this gap by doubling it. So it's just 1 over n, 2 over n, 4 over n in logarithmic number of steps get to this. Now, I'm not telling you what's in these steps, but I'll tell you an inspiration for it. And it turns out that this inspiration, again, came from a completely different area. I'm repeating myself, I know, but that's the main point. In her paper, she gives, credit to this inspiration, to this other wonderful result. SL equals L, here, that's this statement about 2 other complexity classes, basically says that the problem of graph connectivity is solvable in logarithmic space. And that's a problem in other area, in space complexity. So it turns out that this problem, which was solved just a year earlier before her paper, and the method of proof, which looks very much like this, inspired her to give her proof for the PCP theorem. So let me tell you one thing about this result, about this Hastad. I will tell you what the statement and the result is. This problem about undirected connectivity is basically the problem of exploring unknown terrain or exiting mazes. So you can see it's a very ancient problem. It's a very modern problem. It's a problem for all time. You have an n-vertex graph or maze, and you have only local view. The log space restriction means you can just remember the name of the intersection you're at, and you want to get out, or you're in an unknown city, you want to reach your hotel. You don't have a map, you don't have memory. What do you do? And a fantastic solution was given about almost 30 years ago in this paper, which says, well, it's not a big deal, just, go to the next pub, have a few drinks. By then you can make sure that you make random walks in the different intersections. You go around town, and, for sure, you'll wander the city in such a way that not only will you find your own hotel, you'll find every other hotel. And it will not take that long. I mean, if there are n vertices, it will take n squared steps. So it's, polynomial in the size of the graph and requires no memory. And this raises, any such probabilistic algorithm raises, at least in some of us, the instinct to de-randomize it, or to say, what do you do if you don't have random coins, or you don't have beer, or is there a deterministic way of exploring unknown terrain? It's a very basic problem. And just a year before Benor, Omer Reingold gave the solution. He found a deterministic way of exploring any unknown graph with only log space of memory. And only for this solution that took about, this was open for 30 or 35 years, for this to happen, something had to happen in another area, which is the area of constructing expander graphs, and in particular some work that we did a few years before with Reingold and Vadan. And this kind of iterative construction is similar to his iterative construction of SL equals L. He basically transformed any graph, any maze, even planar one, which is very non-expanding, into an expander graph by a series of amplifications, but not of the gap, but of the spectral gap. For those who say, and then he really knows what she did. So that was it. So let me finish. First, I just want to say that a very high-level point, that computational complexity view and definitions, like of proofs and of interactive proofs, but of many other notions, are give us often new insight into them. And let me tell you about other reductions that some of you know, and maybe not in this form. So reductions are about connecting the difficulty of different problems. So here's one problem that people believe is hard, the factoring of integers. And here are consequences of it that don't seem to be exactly of the, they seem to be to have a higher level content. It turns out that if it's hard, then learning of very simple functions is impossible. That we will have a very hard time of proving people are different than NP. It's very hard to prove lower bounds. That randomness is not as powerful as it seems in algorithms. That zero knowledge that we saw proofs are possible. And in general, if we have this, then we have cryptographic systems and electronic commerce and so on. So somehow, assuming computational difficulty and using reductions, you can get statements that are very relevant to understanding basic notions that we are studying, and there are, of course, many more of these. So we want to understand reductions. Reductions themselves should be an object of study, and the obvious or not so obvious open problems to ask is whether we can find reductions for the things we really care about. So it would be really wonderful to base cryptography not on factoring, which can be solved tomorrow, either by some number theorist or by a quantum computer if will be built, but maybe on some safer assumption that P is different than F. In particular, that will require some showing that 3 sub, unlike, well, we know that permanent is hard in the worst case, if and only if it's hard in the average case. We wish we have known such a statement for problems for NP-complete problems, which will be necessary to do this. And so we are led to studying the reductions which would prove such statements. And it turns out that to prove such statements cannot be done with current techniques. I'm not going to define black box techniques, but these are basically techniques that reduce one problem to another without looking at the algorithm given for the one problem. Okay, that's a black box. We use just input-output relation. Right? With the coloring, we just use the fact that the coloring algorithm provided us a 3 coloring, and then we could translate it to a sub-assignment. So what they proved is that at least unless something strange happens, then there are no, the techniques we have cannot prove such statement. And so we need to explore non-black box reductions which use the programs themselves as opposed to their input-output relation. And that basically brings us back to the P versus NP question, because we have to understand programs or computation, efficient computation. So let me end with this. Thank you.
So we certainly have time for questions.
I want to ask if, so you mentioned this remarkable proof of theory, and that proof is based on ideas known as L equals L. So can we just use SL equals L as a black box and prove the TCP theorem?
Probably not at all. I mean, I don't think so. It's certainly in proving results, we are not operating in a black box manner. The proofs themselves may be black box, but the ideas used in the proof often, that's why, I think that many mathematicians, so there is a big project of automating proofs and automating the verification of proof, and a trend that came because of proofs like the 4-color theorem or the Kepler conjecture, proofs that use extensive computer sets and so on. There is a trend to automate and the writing verification of proofs. And one side of mathematics automatically rebels against it, because what they want is not formal proofs. Well, that maybe is good for verification, but if you want, proofs are good if you can understand the ideas in them. And I think this is a very particular example where it's essential to understand the ideas in Reingold's proof, rather than to have some an automatic verifier for it and generate. So I doubt very much that the two problems are formally connected. I think the proof techniques are very, very connected. This amplification idea, and you see it now. Once it's understood as a technique, in fact, you see it in other. Oded Goldreich has an interesting paper, sort of connecting a few other results like this, in particular the Jerome Sinclair-Vigoda proof of the approximation for permanence. What, the approximation of permanence? This is 3 years ago or something. Shortly after Theory's proof. Yeah.
Obviously, on your speculation with respect to the proposition, if there exists for the purpose of NP, there exists a convention, the law exists in the actual convention. Can you say that is false?
Yeah. So I think that, I don't see any reason whatsoever why it should be true. I don't.
That it's false.
What?
You know that it's false.
I don't know that it's false. I don't know that it's false. I would be amazed if it's true. there are conjectures like it, not exactly about gadgets, but about the nature of reduction, like the isomorphism conjecture of Berman and Hartmanis, about the, you know, that reductions, say, between NP-complete problems will always be isomorphisms. You know, there is always a reduction that can be inverted. I'm not stating it exactly right, but anyway, about the nature of reductions, and I think this is far weaker than what you're asking. I don't see any reason that it would be true. I think we are fortunate that so many NP-complete results can be proven via gadget reductions, and so we have them, and so lots of people, in particular people in other fields, can do it. But I don't see a reason why.
I'm just wondering if you could take these very complicated proof techniques that establish reductions and somehow poly them into a formula.
Yeah, I don't know, and I don't think it would be true in general. But maybe Eric has something.
Can I jump in? Yeah. For general polyton reductions, I agree with Avi that I'm not seeing any way that you can prove something like that. But people also look at more restricted notions of reducibility, like AC0 reductions, which make sense for smaller complexity classes. And there basically is a theorem. Anything that's complete under AC0 reductions is complete under reductions that any bit of the output only depends on a few bits of the input. So that's like a gadget reduction.
So that's your paper with Rutgers and Tony Pitasi and what? Published across all the course. So for very simple reductions, but this is a real restriction on the complexity of reduction, you can prove such statements. Yeah.
I guess this is more of a personal question. What is the brightest idea that you had that did not work out?
To come back to New Jersey, right?
I like many of the ideas. I don't know. The right answer for this is what excites me today. You know, it's always something else. You know, I'm going to talk to Mike Sachs in the afternoon, and I'm very excited about that. So the ideas we are pursuing. So let's, yeah. Yeah.
There are polynomial time reductions, and there are more restricted classes of reductions. Are there less restricted, like exponential time reductions that are used?
Yes. There are definitely reductions of different complexities, and they make sense. The restriction on the resources of a reduction come from the understanding of what you are interested in. So, for example, when you want to prove that some problem is not just NP-hard, but maybe that it requires exponential time, then you are led naturally to studying sub-exponential time reductions. When you want to prove that problems are in NC or something like this, in very fast parallel algorithms, you are naturally forced to restrict them to be in log space or in very fast parallel time. You just don't want the reduction to solve the problem for you, right? So when you're proving NP completeness, you don't want to allow an exponential time to the reduction, because the reduction will solve the problem. It wouldn't need the algorithm. So yeah, and people are studying reductions of various restrictions. Yeah. There are even non-deterministic reductions, if you want to say, to have statements about coin P, and there are very interesting non-deterministic reductions between various number theoretic problems. Yeah, there is a huge variety.
Are there any other questions?